Hello, this is for COMP345. This is week 11, slide set 10. This is exception handling, the second part of the second video of two videos for this slide set. So this is going to be about mainly explaining an example I have designed about exception handling. It is more about designing with exceptions and making better use of exceptions than most of what you see in many examples that you may find out there. Okay, so let's go to the slides for a start. As you see, I have my board that is ready with the depiction of the example, but let's start with the narrative before. Okay. So the idea is that we have a boiler. Now, boiler, what is a boiler? Well, first of all, the example of a boiler is one of the typical examples of a reactive system. So a boiler in the industry is basically you have a tank, you have an electric element or heating source in the tank. It's basically heating up the liquid, normally a liquid that is in the tank. And potentially, well, or not, if this tank is closed, tightly closed, then the pressure will rise as the liquid is going up in temperature. So you have the notion of a sensor, and that's what, my example is very simplified. You have a sensor that reads the pressure in the tank, and then you have an actuator who's instructing a valve so that if the pressure goes above a certain security level, that the pressure valve will be open to release the pressure so that the tank does not explode. Okay, so you have to understand the example is extremely simplistic. Don't assume this is how an industrial boiler controller is done, just to show a good use of exceptions. Okay. So that's the idea. You have a boiler. I'm not even considering the heating source turning on or off. I'm just considering the pressure sensor and the pressure release valve. Okay. The pressure is rising, and then the valve is used to release the pressure and eventually have the controller shut down, and then there's an emergency situation and so on. Because one of the things is that, of course, this deals with exceptions. So the sensor and the valve are two devices that can throw an exception. That's what is the premise of my example. So basically, I'm simulating the valve and the sensor. And as the software interacts with them, there's a possibility they will misbehave and throw an exception. Okay. So the boiler itself is connected to these pieces of equipment, which then can actually throw exceptions. Now, it's imagined that the people that design this piece of software, they say, we don't want to deal with exceptions in the boiler controller itself. Even though these pieces of hardware are throwing exceptions, we don't want the design of the boiler to have to deal with exceptions. Okay, so you want to somehow shield the boiler from the exceptions. How do I do that? Basically introduce a new layer in the design. Let me go back to stopping the share. So this is my boiler here, the code for my boiler. And here's the hardware layer where I have this pressure reading, this pressure sensor, and the actual pressure release valve. So of course, the boiler is going to want to read the pressure because it needs to, gather a log of the pressure over time in the container in the boiler. So it's going to gather a log of information. Okay. So as it, for example, asks the pressure sensor, what is the pressure? When the pressure sensor gets the answer, then it will read this into a pressure log file. Okay. If the pressure goes over a certain level, then the boiler is going to tell the actuator or the pressure release valve to open. Then it's also possible that as if the valve is stuck, that it will actually throw an exception. Okay. So the boiler can try to open the valve to release the pressure because the pressure is too high. And then if the valve is stuck, of course, then we are in an emergency situation where we need to evacuate. So as this is actually throwing exception, then the boiler needs to take an action to evacuate the place, okay? Because the boiler is going to explode because you can't release the pressure. Now, because we don't want the boiler to deal with the exception, then what I do is I design a layer here between the boiler controller and the boiler itself. I design a layer here that is going to have components that are going to get the exceptions and somehow consume these exceptions or catch these exceptions so that the boiler can continue executing and not even be aware that there were exceptions that have been thrown. Okay. Now, what's going to happen also is that I'm going to design these exception handlers classes so that as they receive an exception, they will actually write the fact of receiving the exception is going to make them write a record in an emergency log using the exception that were thrown. So I'm going to create my own classes of exceptions, objects that have been thrown by these here, which are going to contain some information about the state as the exception was thrown. And then these here will receive these exceptions. And then this information they will receive through the exceptions is going to actually be used to write a useful entry in the emergency log. Okay. Now this act of actually having some exceptions that contain information that you can act upon or use to act upon as you are processing the exceptions. It's not something that you see very often, but that's why I'm having this example to show that it can actually be done. Let's go back to the example. So it's essentially the same thing I have on the board. So my boiler here, we don't want the boiler to deal with exceptions. Okay, even though my sensor and my pressure release valve, when I interact with them, for example, it's possible I call get pressure on my sensor controller. On my sensor here, basically I'm simulating the sensor and I'm simulating the valve, of course. So if I call get pressure from my sensor, it's possible that it's going to throw an exception because it's misbehaving. And I don't want, even though the boiler is calling get pressure, I don't want it to actually, for the exception to reach the boiler. So that's why I designed this intermediate class here that is between the boiler and the pressure sensor, so that when I call pressure sensor from the connector, which I call the connector, it is going to call get pressure of the pressure sensor. If this throws an exception, then this method here would catch the exception and then somehow let it continue let the boiler continue executing, even though an exception has been thrown and the boiler is not even aware that there was an exception being thrown. All the exceptions are caught in this yellow layer here. So it's essentially this yellow layer is an exception handler among other things. So you will see that we have catch in the get pressure and the open and close. We also have catch that are catching the exceptions that are thrown by these methods here by the hardware things that I'm simulating. Okay, let's go forward. So first thing I'm explaining here is the hierarchy of exceptions I'm creating. Now, it's important to realize that in C++, unlike in Java, you can throw anything. Okay? You don't have to throw exceptions. Anything that is a value is something that you can throw. You can throw 2 if you want. Okay? Whatever is a value, you can throw it. Then it can be caught by a catch that is catching that type. So you could have a catch that catches ints if you ever, for example, as I said earlier, throw a value int like 2. So you are allowed in C++ to throw and catch exceptions of any or values of any type. Here, I'm designing my own exceptions, which happen to be subclasses of exception. It would not have to actually be a subclass of exception, but I made them so. Here, let's see my hierarchy. So you see that these are all my exception classes. They are all subclasses of exception. Then you see that I have the hardware exception, which is my superclass of all my exceptions for my design. Then I have actuator exception, which are the exceptions that may be thrown by my actuator or my pressure release valve. Then I have sensor exceptions, which are the exceptions that can be thrown by my sensor. Sensor can throw negative pressure exception if the pressure that is sensed is below 0, which in my design should be impossible. Then it's just basically an exception. If the value read is below 0, then it throws a negative pressure exception. If the value is over a certain very high limit, which is impossible to read, then it would throw an overload pressure exception. Okay. If you are calling the actuator, let's say open or close, and it cannot do the operation, then it basically calls or creates a stuck valve exception. Okay. Now you have to understand that this fact that the pressure or the actuator are misbehaving, and I'm simulating that using a random number calculation. So that's the design of my hierarchy of exception classes. Now you see that in my classes, I actually have members. Now that's what this thing I want to add in this example is that here you start having in this example members or data members that are stored inside of your exceptions. So exceptions are objects in this case. So they can store a value that can be made useful in the processing of the exception. Okay. In many cases, an exception, the only thing that it would contain is a string that the program actually puts into the object, and then this string is contained in the exception and can be used. For example, if you want to print out the string that is contained in the exception to hopefully, when the exception was created, contain a descriptive message of what happened to when this exception was thrown. Here, basically, I do the same, except I have more details about, for example, time. So when the exception is thrown, I actually record the time in the exception so that I can know when this exception was thrown. So that when an exception is thrown, whatever is handling the exception later on has the record of when this exception was thrown. Eventually, I'm going to use that, of course, to put it into my log file here. Okay. Other thing is, for example, for my actuator exception, it actually stores what was the state of the valve when the exception was thrown. For example, the valve, yes, the valve was stuck, but was it stuck closed or was it stuck open? Okay. In my sensor exception, I store also the value that was read. So yes, this was it was either a high value or a value that is above the threshold of what can be read by the sensor, or a negative value. But what was this value exactly? So this is something I actually store in the exception. I also overload my stream insertion operators on my exceptions. So that's I will use to actually output, literally use my stream insertion operators to output the exception inside of the emergency log file. So you see that you can actually use your, it's not often that you see an example that uses exceptions as classes that contain data, that you can define their own behavior and so on. That's essentially why I designed this example. What's happening here? Okay. Now this is the code for, I'm just going to move this around here. This is my view. This is the code for my hardware exceptions, the subclass of exception. It has the time where the exception was thrown. And another thing is important to in C++, every exception that is a subclass of exception has this member named what, which is essentially a string that is contained inside of the exception, much like what you have in Java. Okay. So if you call this exception dot what, then it basically prints out the string that is stored inside of the exception. Okay. Of course, you can override this method, and that's one of the things I do in my code here. Then I have my all my subclasses of my exception classes, and they each have, some of them have data members, for example, value read and the state, as I've just explained before. And I have my friend insertion operators for my actuator exception and my sensor exception. As we saw earlier, the stream insertion operators must be free operators, but here I make them, of course, friends of my exception classes. That's it for this one. Then here you see the actual implementation of some of my methods inside my exceptions. So this is here how I actually get the time, the system time to actually instantiate my time value inside my exception. Actually here, this is how I override my what function for my hardware exceptions. Basically, I store or I return when you call what here, instead of returning the string that is contained in the exception, it actually returns the name of the class of this exception, pretty much like what you have in Java also. Here, this is just to show that you can override the what function to have specific behavior. Okay, and then here you have my stream insertion operators, which are basically outputting, for example, for a stuck valve, you would print out the state of the valve, for example, open, and then you would have at, and then the time when this exception was created, and then what is the type of the exception by calling this here, which is printing the type of the exception. And similarly to my stream insertion operator for my sensor exception, which prints the value read by the sensor at the time where it threw the exception, then the time where the exception was thrown, and then the type of the exception. So here's very simple. Again, I don't claim that this is a real industrial boiler controller, not at all. So my boiler is actually containing, where's my boiler class here? My boiler is containing some my two files, which are output files, emergency file and pressure report file. That's my emergency file here, my pressure report file. Also, the state of the boiler is member of the boiler. We will see that depending on what's happening, the state can be, as we say here, boiler state can be either safe, unsafe, or critical. It is normally safe if an exception is being thrown by the pressure sensor, then it goes into unsafe. Then if it is unsafe, then it's going to try to open the valve to relieve the pressure. Then if it is, the valve is throwing exception, then it's going to be critical, in which case it's going to want to do an emergency situation and tell people to evacuate. Okay, so here I set up my file. So you see that this is creating some file streams here, which I'm going to use to actually output. For example, my exception output is going to go to the files because I have file stream insertion operators for my exceptions. Then my boiler has a start. What does start do? It's basically calling forever. It's calling get pressure. So you see that it's very dumb. Okay, it's just basically reading the pressure forever. Of course, here what I'm calling is get pressure of what? Get pressure of PS. PS being PS is the pressure sensor connector. Okay. So the boiler itself is not connected to the sensor. The boiler is connected to the pressure sensor connector that is itself is connected to the sensor. Okay. So that means that when the boiler wants to get the pressure, it calls this component here. The only thing that this here is the boiler is aware of is these connectors here. It's not aware that it has even connected. These are connected to actual sensors. So this calls get pressure to this, and then this call gets pressure to this. This may throw an exception. This will catch the exception. With the exceptions, we'll never get here. Okay. Okay, so it's calling get pressure of the pressure sensor connector. You see here, I don't have catch because the catch is actually in the pressure sensor connector. Then when I call get pressure of the connector, so the pressure connector, pressure sensor connector, get pressure. Get pressure of the pressure sensor connector, which is called by the boiler. What it does is that you see here, I have a try that is going to catch the exceptions from the sensor. Okay. Now so my pressure sensor connector, of course, it contains somehow a pressure sensor to which it's connected to. It also contains a pointer to the boiler. Why? Because the pressure sensor connector can do two things. It can read in the file that is in the boiler, and it can also act upon the state of the boiler. For example, if an exception is being thrown, as you're calling get pressure, it's going to tell the boiler to be in the unsafe mode, as we see here. So it's reading the pressure. It's trying to reading the pressure here. And then if this actually is throwing an exception, then you will be catching the exception here. Okay. If this does not throw an exception, then it actually reads into the pressure report file of the boiler to actually, you see this is B dot pressure report file. So that's one reason why it needs to have a pointer to the boiler to be able to read in the file of the boiler. And then every time it reads, if everything goes well, it just basically reads to the file, reads the pressure reading to the file. If an exception is thrown, then it does that here. The catch sensor exception here, then the exception here is the exception E. So it basically outputs E into the stream emergency file. So basically it takes the exception, uses the stream insertion operator on this exception, and then sends this text representation of the exception into the emergency file. So that's what this line is doing here. And then tells the boiler, put yourself in the unsafe state, and then tells the boiler to shut down. Okay. You see here that my catch here is doing something very important that is a result of an exception having been thrown. Okay. That's what this should be the essence of what is in a catch block. Something very wrong have happened that you cannot recover from. If the valve is stuck, there's no point in this boiler to continue executing because it cannot deal with the valve being stuck. The only thing you can do is to record what happened for the investigators after, and then tell people to to evacuate. It's the only thing you can do. You see, exception is something very wrong that potentially you cannot deal with. Some exceptions you can deal with, but like, for example, if the get pressure, you get the pressure and then eventually it throws an exception, then what you can do is what it does here, try to open the valve. If you open the valve, then the boiler can continue executing. Okay. But if the valve is stuck, then that's it. There's nothing else you can do. Okay, so call get pressure, trying to read the pressure from the sensor. If everything goes well, record the pressure and then read the pressure again, until this may throw an exception, in which case the boiler is put himself into the unsafe state. Okay. Okay, let's move forward. Then here, I have my code for the pressure release valve connector. So for example, if I try to open the valve as a result of, the boiler wants to open the valve to release the pressure, it tries to open the valve itself. If the valve itself returns an exception because it is stuck, then it will go here and basically tell the boiler to put themselves in the critical state and then write the exception into the emergency file. Okay. So that's the example. So going back to the beginning here to explain, to give a sense of why what's the deal with this example. The idea is that you're here designing a boiler, and the idea is that you don't want the boiler to ever be aware that exceptions are being thrown. Okay. But you have some components that will throw exceptions. So what you have to do here in this case, or what I did in this case, is to design this layer that will actually catch the exceptions. Okay. Essentially, that's an exception handling layer that I've put by creating objects whose one of their goals is to shield the boiler from the exceptions. Interesting aspect of my example on top of this is that my exceptions are gathering information, and when these exception handling classes are receiving these exceptions, when they catch the exceptions, they take actions such as reading in the emergency file, and so on and so forth, and then tell the boiler to put themselves in a state and so on. Okay. So I wanted to show here more dynamic aspect of dealing with exceptions. Okay, so let's go to the conclusion of this exception handling lecture. So these are the words of Bjarne Strustrup himself that I took somewhere in an interview over the internet, which I found was very interesting. So the interviewer were asking questions such as, does exception handling mechanism solve your problems? His answer was no, it does not solve problems. It's just a tool that you use to help you solve problems. Okay. See, that Strustrup is very kind of a pragmatic person. He's providing with C++ is a very notorious tool. It gives you a lot of power to solve a lot of problems. It's a very powerful tool, but there's a lot of wrong ways that you can actually use C++. That's a very notorious tool for that. It's like when you have power tools in your, you might be a woodworker using power tools. Some of them are very dangerous. Some of them you have to know exactly how they work if you want to use them effectively and safely to actually do your job. C++ is a tool like that. It's a tool that you use, very powerful tool. But if you don't know what you're doing with this tool, it's going to bite you. You're going to get hurt. So yes, he's basically telling you exceptional handling. Does it solve your problems? He says, no, it's just a tool that that helps you solve the problem if you know how to use it correctly. Does the exception handling mechanism provide a radically new way of dealing with errors? Basically says, no, this concept has been there for a long time. It is a very well structured mechanism that helps you to deal with it in a consistent way. Okay, so that it's very explicit how you should actually deal with this notion of exceptions or errors. Gives you a very well organized mechanism by which you deal with errors. Give you a standard way to deal with errors. He also said things like the exception handling mechanism makes it easier to adhere to good programming practices. It is a very structured way to actually deal with the same kind of problem. Before we had exception handling, as I hinted at in the beginning of the lecture, you had things like error codes. This was kind of the Far West back then because people had their own view of what is an error code, had their own coding for a lot of different error codes, and you had to know what's the meaning of all of these codes in order to use the functions that were using error codes for each of these different libraries. So there was a lot of different ways people were doing error codes. Okay. Now there's a standard way that you should expect what is an exception being thrown, and there's a standard mechanism embedded in the runtime system to actually deal with them all in the same way. Okay. It's a way to normalize how things are handled. Erroneous situations are handled by a program. It gives the error handling more regular style, so that people don't have their own design ideas every time they deal with error codes, for example. If you're using C++ with exception handling, you have a try block, catch blocks, so on and so forth. So it's all dealt with in the same way. Makes the code more readable because it's expected. It's something that people expect. Okay. Also more readable because it tends to actually separate the normal execution from the abnormal, the result of execution of an abnormal, the reaction to an abnormal situation, which is located in the catch blocks. If you don't look at the catch blocks, then you see the code for all the normal situations. If you wouldn't have catch blocks, then these two pieces of code would be in the same place, which might be confusing to read. And of course, error prone to change. Okay, so then another interesting question is, because C++ is, it's designed to be extremely efficient. So a question becomes, did we or did the designers of C++ add something, namely error handling, that made actually your programs run slower or consume more memory? Of course, anytime people discuss about C++ features, they are concerned that you're not adding something which makes the language run slower or consume memory. More memory than it should. So the answer to this is the way that it's implemented, there's very minimal performance cost. If your program has exception handling code in it, and then you execute this program, and then for this particular run, if it does not throw exceptions, there's literally, you can't say there's zero overhead, but the overhead of having exception handling code in your program is extremely limited. It will, however, make the compilation of the code a little bit slower, which is acceptable because here we're mostly talking about efficiency of execution, not necessarily compilation. If an exception is thrown, so here I was talking, if exceptions are not thrown, is there an overhead? The answer is extremely minimal overhead. Okay. If an exception is thrown, is there overhead? Yes, there's some kind of overhead, but overhead is also minimal in the sense that you might say, oh, it's going to have to do a stack unwinding. Well, there is still stack management that is happening in normal execution. Stack unwinding versus normal stack operation, is very, very similar. Okay. What is really, I was about to say what is really, that has a lot of overhead, but it's not really that it has a lot of overhead, but the most of the overhead involved in exception handling is the search of the appropriate catch. Okay. As you throw the exception handling mechanism is going to basically try to find, it's doing a search of a catch. Okay. So it has somehow a record inside of the code, some kind of record of where are the catches in the code. And somehow the exception handling mechanism is doing a search of a catch block somewhere. So this search is what is the most costly operation in the whole exception handling mechanism. So essentially in the program, the more you have a higher number of catch blocks in your program, the more costly is this search operation. Okay, so that's what is the most, it's not very, overhead of this search is not very high, but this is the most of the overhead of the exception handling mechanism. Of course, here I'm talking about a search of catch blocks. Of course, if you're doing a search, that means that there's some kind of data structure somewhere in which you're doing this search. So of course, this data structure must be there in order for this search to happen. Okay, so yes, if you enable exceptions in your program, then there will be some data structures that are going to be created for this mechanism, especially the search, to actually happen. Okay. One of the things I mentioned in a previous video, when you declare in your function, you can declare throw and then open, close curly bracket. That basically tells the compiler the code of this function cannot throw an exception. So that makes it so that when the compiler is compiling this piece of code here, it will not generate any entries or spend any time to deal with exception inside of this code. So the more you throw open close bracket on some of your methods, the more you're actually saving time at compilation, and the more potentially, the less potentially there is some entries in the more easy would be the exception handling at runtime. Okay. So that's one of the advantages of putting throw open close parentheses between at the end of your functions. So when is it that, what is the worst case? What is it you want to avoid? If you want to avoid the overhead of the exception handling mechanism, so you should avoid as much as possible that exceptions are thrown. Much of the overhead is when the exception is thrown, and then the exception handling mechanism starts doing this search. Okay, so you want to have as less exceptions that are being thrown. So the rate at which exception has been thrown should be as low as possible. Plus, you want to make sure that every time an exception is thrown, that the number of catches that you have in your entire program is as reduced as possible. The more catch blocks you have, the more it's going to increase the overhead of the exception handling. Okay. So the worst thing you could do is that inside of a specific method that runs, let's say, all the time, then you would have a very high rate of throwing an exception. And then you would have a lot of catch blocks inside of this function, or this function is called by another function that has itself a lot of catch blocks, and so on and so forth. Okay. So every time an exception is thrown, the more there are potential catch blocks that can catch this exception, the more it is costly to actually resolve the exception every time it is thrown. So that's what you want to avoid, to have reduced amount of code that throws exceptions very frequently, and that the resolution of the exception to find catch block is complicated because there is a lot of potential catch blocks that can be the solution to resolve the exception. So what is another thing is, well, I suppose that you've figured out by now that especially in C++, if you want to design code that is exception safe, what I mean by exception safe is, for example, we saw that if you design code and it can throw exceptions in C++, very likely it makes it more likely that you may have memory leaks in your program. So if it's a very important concern for you in the design of this program, adding exception handling is going to be very problematic. So dealing with exceptions also is a design issue. You have to be very careful, especially in C++, to organize your code correctly if you don't want to have problems as a result of exceptions having been thrown, such as memory leaks. Okay. So you have to be aware of how it's working and what are the potential problems leading to it, and you have to design your program so that these problems are not happening. Essentially, you have to invest more time to design your code so that it is exception safe. And that's probably what is the most costly in using exceptions, the design time that you have to invest in it. Especially if you should always avoid, as we mentioned earlier in a previous example, to have your constructors throwing exceptions. Even for destructors, it's even more of a problem, because if your destructor throws an exception, that means an automatic memory leak. Okay? If your class contains pointers, you call the destructor, it throws an exception, your parts of your objects were not freed, and you have an automatic memory leak. Okay. As I mentioned earlier, you want as much as possible where the exceptions are being thrown. You want to have as less possible in the vicinity of this error, of this exception having been thrown. You want to have as less as possible dynamic memory allocation that is happening. Okay. So that's it for this lecture. Thanks for passing by.